Okay, moving on to wave optics, chapter 33. So this is problem number 10. It says light of wavelength 620 nanometers illuminates a diffraction grating. The second order maximum is at an angle of 39.5 degrees. How many lines per millimeter does this grating have? All right, so this is a problem about a diffraction grating. So we know that the diffraction grating has multiple slits cut into it. So that's our diffraction grating, looking at it in perspective. And then I'm drawing here the screen. The dashed line represents the center of the diffraction grating and the center of the screen. We know what pattern we're going to get on the screen. We get a pattern with bright fringes and dark fringes. That is a pattern with maxima and minima of the intensity of the light that it's incident on the screen. So the central maximum is called the m equals 0, or central maximum. Then we have the m equal 1 maxima, m equal 2, etc. And the problem is telling us that the angle that a line from the center of the diffraction grating to the location on the screen of the second maxima, that line makes an angle of 39.5 degrees. That is the meaning of second order maxima that we have over here. Second order means m equal 2. So knowing the angle at which the second order maximum is located, then we can use the equation for diffraction gratings. This is the same equation that we have for a double slit situation. Just remember that the small angle approximation doesn't work for diffraction gratings most of the time. So in this equation, the m can be 0, 1, 2, 3, any integer, and it represents the location. The angle theta sub m represents the location of the bright fringe, m equal whatever number. So the d in this equation, lambda, you know what lambda means. D in the denominator is the distance between the slits in the diffraction grating. Again, the diffraction grating has multiple slits through which the light is going to be able to go through, and the distance between any adjacent slits is d. The wavelength given by this statement of the problem is 620 nanometers, which must be written in terms of MKS units as 10 to the minus 6 meters. Every nanometer is 10 to the minus 6 meter, minus 9, sorry. Every nanometer is 10 to the minus 9 meters. And the problem is telling us that theta sub 2, for m equal 2, the angle theta 2 is 39.5 degrees. That's because, again, we're talking about the second order maximum. So you can see that in this equation we can solve for the distance between adjacent slits in the diffraction grating, and that should take us to the final answer very easily. So let's focus on solving for d. So sine of 39.5 degrees equals 2, because m is equal to 2, times lambda, 620 times 10 to the minus 9 meters, divided by d. So putting these numbers in the calculator, solving for d, we get 1.95 times 10 to the minus 6 meters, which I'm going to write now in terms of millimeters. Remember that 1 millimeter is 10 to the minus 3 meters. And the reason for that, to use millimeters, is because we're going to try to get to the final answer, which is asking us how many lines per millimeter, how many slits are there in the diffraction grating in a length of 1 millimeter. So if we take 1 millimeter distance, we have multiple slits in that distance that fit in that distance. The distance between the slits is 1.95 times 10 to the minus 3. So the question is, how many slits in that 1 millimeter? How many lines per millimeter? So easy to find, right? Because if in 1 millimeter, if the distance that we have is 1 millimeter and the distance between slits is d, whatever d is, 1.95 times 10 to the minus 3, the number of slits that you can fit in that distance is 1 millimeter divided by 1.95 times 10 to the minus 3 millimeters. Put in the numbers in your calculator and you should get 513 lines fit in 1 millimeter, or 513 lines per millimeter. All right, that's it. See you in the next one.